Okay, I'm going to post a link. Use the posted link, please. Is anyone in Miss Danier's marketing? Whoa, just turn that off. Are you guys giving presentations to my block F? Someone is. Someone is. Well, make sure. So you got her next, right? Next block? Anyone got her next block? Yeah, are you giving a presentation right away to my block F? Do you know? Can you just make sure to relay the information they have to get to my class right away? Because I got a test, so I can spare like 10 minutes in the beginning. That's it. She emailed me, and I emailed her back. I don't know if she got my info, so that's the one. Hey, I was just drinking a coffee. That's why it's down.
Don't worry, that's not why I even came in
Okay.
here. Have you seen Jay this morning?
Who?
Jay.
Jay, I haven't seen him. No.
Never seen him. Okay.
Yeah. Oh, okay. I'll send him your way. Okay. Okay. Give me a sec. Thanks for being patient. Okay, while I'm about to write down what it is, why don't you write down everything you remember about, don't tell me, but write it down. This, you can title Frictional Forces. Write down everything you remember. Write it down. Everything you remember about frictional forces. Okay. Frictional forces.
Like the same thing as physics.
Yes, and we did all of them the same room.
Okay. You're supposed to be talking about friction, not Friday night. Okay. Force of friction. What is it? What's it dependent on? It's So remember the following. First of all, again, people write it differently, but that's the way I'm going to write it. Represents the force due to friction. A little subscript there to remind us of that. Obviously, it's a force, so it will have units of newtons. When I write these down, it'll make more sense. So I'm going to use this in the formula to represent how rough the surfaces are. I'm going to use the word plural, surfaces. It includes both. It's a measurement. You can think of it as a measurement of how rough the surfaces are. No unit. It's known as this coefficient. Of friction. M obviously is mass in kilograms. And G, when we're using the calculation G, we're just going to use the absolute value. It's 9.81. Acceleration due to gravity. This can change obviously on whatever planet you're on, but 99% of our questions deal with Earth. Acceleration due to gravity. It is 9.81 meters per second squared. Alternative unit, you know what, I'll put it in red just so you can see it more clearly. Meters per second squared, or, and we'll get more into this later, newtons per kilogram. Alternative unit. Okay, so we know from measurement, we know from experience, we know from testing that the friction depends on how, first of all, rough the surfaces are. So it depends upon this coefficient I talked about. One more thing I forgot to mention, sorry. Fn is the normal force. Not the net force, the normal force. This part here. That means perpendicular to the surface. Always perpendicular to the surface, which may or may not be a level surface. And obviously it's in newtons, it's a force. Okay, so we know this from measurement. Friction directly is related. Directly related means if you multiply if the coefficient here doubles, the force doubles. That's what we mean by directly proportional. And we know that the force of friction is directly proportional to the normal force. What is that normal force? Let's take a look just on a surface. Got a block. Mass M. It's going to experience a force of Fg, force of gravity. Okay, which we said is just mg. In this, this is a level surface. In this particular case, the normal force is the force that the floor pushes back with. So the floor pushes back with an equal and opposite force. That's our Fn. And in this particular case, this is not always the case, but in this particular case of a level surface, they're equal in magnitude, not in direction, obviously opposite direction, but equal in magnitude. Okay. So make sure you understand this is for a level surface. No forces, no other forces acting. So nothing's pushing down on it, nothing's lifting it up. No other forces acting. Right? If I were to push down on this, there'd be more pressure on the block. If I took a hand and left, my hands are not that great. If I put a hand here, you don't have to draw this in, but if I push down with a hand with a downwards pressure, that would increase the floor's, the force that the force experiences, the force that the floor experiences. It would push up with a greater force. Okay, so we'll deal more with that later, but I'm not talking about any addition of forces other than the force of gravity on the block itself. So in that case, this is true. And go back to this equation. For a level surface, again, it's important you understand the conditions under which you apply an equation. Conditions will change the equation. In this particular case, this is always true. This is the general equation, always true. That's what I mean by general. In all cases, whether it's a level surface or not. This is what the equation reduces to for a level surface, mu Fg. Because as I said here, they're equal. F and F are equal in magnitude. So that's why you're used to writing this. This is probably what you're used to writing in grade 11 or from physics 11. That is the equation for friction as far as you know. In the limited sense. In what limit? Again, I'm saying it, level surface. No other forces acting. Nothing pushing down on the block or pulling on it. Okay. Okay. On a side note, Fg is referred to you know this already. It's the force of gravity it is in newtons. It's a force. You'll hear it mentioned or referred to as the force due to gravity, same thing. It is equal to mg. Again, g we spoke about, g is 9.81. We're going to use the absolute value for our calculations. Okay. This is obviously the average on the surface of the Earth. So this is applicable on the surface of the Earth. On the moon, this is the Earth. We don't usually add that subscript because we simply stick with the Earth 99% of the time. But G can change. Mass does not change. Mass is a constant on any planet, but the acceleration can change. On the moon, it's 9.81 divided by 6. This is an approximation, right? Meters per second squared. That's why you see, I know I don't want to hear any arguments, but when you see the footage of astronauts on the surface of the Earth, you see them bouncing up and down slowly. Don't say it's slow motion, it's real, okay? Don't want to hear arguments about fake moon landing. When they're on top of the surface, they jump up, and you'll see when they come back down, it's a very slow ascent, and that's because of this. when Elon and company gets to Mars, so this is the moon here. When they get to Mars, Mars will be a little bit stronger, but still weaker than the Earth. By how much? Yeah, 1/3. 1/3. So the point is what? The point is this equation will hold regardless of where you are, whether you're on the surface of the Earth, Moon, or Mars. But what changes? That changes according to wherever you are. We usually just apply it on the Earth. This does not change. This is a constant. Mass is a constant. Mass is a constant where? Everywhere. Now, can we prove that? No, but so far so good. Because mass is just a measurement of the quantity of matter, the amount of atoms in it. Okay. Okay, so here's the hard part. Now you remember what you were taught in Physics 11 about friction, but you realize the restriction for this is, again, level surface. Let's just repeat it because it's going to change in a minute here. Level surface. Now we're going to look at the more complicated case of friction on an incline. What is that? Well, it's just a hill. You can think of it as a hill. Anything that looks like some slope, even a ski slope, that would apply. Okay, so let's draw the incline. Okay, we're going to work with, I'll draw that smaller one, but perfect for it. Come on, dummy. Program. Hard for me to see, but anyways. I want to draw a right angle triangle. That's what I'm after. Come on, straighten up. Okay, right angle triangle. There you go. That's an incline. That's a hill. That could represent the side profile of a ski hill. Or something similar to it. Where there's an angle here, I'm going to use a generic angle of theta. Okay, let's put a block on this. Of mass m. It says of mass m. And nothing changes as far as gravity. Gravity will always be, yeah, it's always going to be down. That's my FG. I'm going to kind of exaggerate the size of gravity so you can more clearly see. However, the normal force, this is the surface here, right? The normal force direction is always perpendicular to the surface. So the normal force is no longer sticking straight up. Yeah, it's perpendicular to the inclined surface. So it's, when you draw it, give me a sec here. We'll straighten up in a minute. When you draw it, you have to draw it so it's perpendicular, think of this as a line that's parallel to the incline, has to be perpendicular to that dashed line. That's my FN. Why is that important? Because keep in mind now the value for the friction is going to be less, going to be lessened. You can see FN, the way I drew it, it's hard to see maybe, but FN is smaller than FG. This is always true for friction. That's what we're after. What's the friction of the block or what it experiences on the incline? This is now less, this is less than FG. And why is it less? Because if I were to draw it out, I were to draw the component of FG out, now I'm going to represent FG in terms of, I'm going to draw the components of FG out that are perpendicular to each other. Why? Because it forms a right angle triangle. This is math I know how to deal with easily. I'm going to draw this one as purple. Okay, so what am I going to label this? This here, this component here, this is still FG. I'm not finished. I got to add something to that. This purple one is still FG, but obviously different than FG, but a component thereof, perpendicular components. This green FG, it is perpendicular to the surface. I'm going to remove that in a second. I'll keep it in there. So we're going to call that FG perpendicular. That little symbol there, that upside down T, that means perpendicular.
It's an upside down T, correct?
Upside down T means perpendicular. And then we'll go back to the purple component. This here, see what I'm highlighting? This vector here is parallel, supposed to be parallel to the incline. So we're going to call FG parallel. I'm going to write these out here. FG, perpendicular component, of what? Of FG. And what about this parallel component? FG with railroad tracks, that means parallel. Two parallel lines. So this is known as the parallel component. Can you see the purple? Okay, now I'm going to give you something. I can actually, you guys don't even have the geometry like you used to do. It's not your fault. But they used to teach geometry as a whole, complete unit. My day, it was a complete course. It's fundamental. I don't know who got rid of it in math, but they're wrong. Okay, it's like part of the foundation of Western Civ. So why would? And plus, it's very useful. In this case, now we can go through that, blah 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 blah. But suffice it to say that this angle here, you just need to know it. Okay, you want me to prove it, I can do it later. But that angle there, see what I just drew?
Yeah.
It's the same as the angle of the incline. Did you get it? That's a necessary fact. So this, look what I did here. So this angle here between the green perpendicular components, between there and between this red vector here is FG. I'm making it a little messy so you can see. That red arrow is FG. So between the FG perpendicular and FG, you've got angle theta, the same angle as the incline. It's the same angle. You can prove that geometrically. Okay? It stems from the fact that part of the fact that that's a perpendicular angle there. Okay, now here's what you're going to do. Don't tell me. If you don't mind the color, well, we'll stick with white. Go back to white. It's easier to see. I want you to find the following components because these are really important, especially for us, the perpendicular one. I want you to find FG perpendicular and FG parallel. You can talk amongst yourselves. Don't tell me though. I want you to try to figure it out. Express the perpendicular and the parallel components in terms of the hypotenuse, which is FG, and the angle theta. So you got some expression on the right. It's going to make use of, there's your hint, trig functions. So make use of trig functions and FG and the angle to come up with an expression. Is there a way of rotating objects in these programs? I wonder if I can do that, then I can show you more easily. I'm going to redraw the triangle here. Yeah? Yeah. Yeah? Do you like my different colors or no? I try to be colorful. I'm a colorful guy. What can I say? I'm just redrawing the FG triangle. I just redrew the triangle for you. You can make use of it. Okay, so this side here, let's just label this. FG is opposite the right angle, so it's a hypotenuse. FG parallel is opposite the angle in question that we're going to be given because we'll have the angle of the incline. So it's the opposite angle. Opposite. This is the opposite side. Opposite the angle. And whatever's left over must be the adjacent since it's a right angle triangle. So I'm going to make use of the cosine and the sine. Cosine comes first because I'm interested in the perpendicular first. Let's write it down. Cosine of the angle, you know, is equal to the adjacent over hypotenuse. Which in our particular case is FG perpendicular over FG. I want to solve for the FG perpendicular. What I want. So you multiply the FG by the cosine. I can put it in front or in back. It doesn't matter. It's like, they're just numbers, right? 2 times 3 is the same thing as 3 times 2. Right? That doesn't matter the order. I'll put the FG in front. That's where we usually put it. So you want to highlight this. This is going to come in handy. Back sore. That's the expression of FG perpendicular in terms of FG and the angle of the incline. Okay, that's the first point. Second point, use the sine function. Sine is equal to opposite over hypotenuse. Opposite, in our case, in this particular case, is FG parallel. Hypotenuse is before is FG. Rearrange, I want to solve for the FG parallel. This is used throughout the questions on inclines. So again, just multiply the FG by the sine of theta, sine of the angle of the incline. That's our expression for FG parallel. Okay. So just take a minute to see what the logic is. If you're not getting it, take a minute, look at it. Because I'm going to make use of those two rectangle expressions, the ones that I highlighted with the rectangle. Particularly the first one. That's the one I'm most interested in at this moment. Now come back to the FG parallel. I'm going to highlight this. This is the one I'm going to FG perpendicular. Okay, let's revisit what we know. This is the equation for friction. Why didn't I write mg? Because it's not a level surface. This is the general expression. We can demonstrate this. This is always the case. Whether it's an incline or it's a level surface or any other particular situation, that expression holds. So in this particular case, we're going to write down the condition. Condition is incline or incline. Friction is equal to, obviously, mu Fn. That doesn't help us in this particular case if we're given Fg. If we're given Fg, we need to know what Fn is in terms of Fg. Well, Fn is just equal to F perpendicular. You go back to this diagram here. Look at how I drew them. I drew them, well, I should have drawn, if I drew them to scale FG, should have been drawn equal length, but it's hard to do that. Hard to judge that, but they are equal and opposite. If the block pushes down on the surface, right, the surface is going to push back. But what does the block push down on the surface with? It doesn't push down with the full weight of Fg. The block pushes down on the surface with the perpendicular component. The parallel part won't contribute to it because it's parallel. So that means for every action, there's an opposite and equal reaction. The floor, in this case, the incline pushes back with an equal force in magnitude. That's why I'm able to write what I just did here. That F perpendicular is equal to the normal force. What's that equal to in terms of Fg? Just equal to Fg times, go back to here, it's this expression here, times the cosine. That's your new expression. For what? For an incline. Know the condition, because the condition sets the restrictions of the formula. That's our new expression for friction. Now let's try to turn it into something that's a little bit more familiar. What is that? That's just mg. It's You want to write it like that? I'll write it either way, but essentially it's this. So why is that useful? Because this part here is the friction on a level surface. Well, what does that make this factor here? It's a correction factor. It corrects for the fact that we're no longer dealing with a level surface, but an incline. How does that affect the overall friction? Well, if you know your math, cosine of theta is always less than or equal to 1. It maxes out at 1. Let's just review. When does it max out at 1? Cos of 0 is 1. Cos of 0 degrees. What is that? 0 degrees. What kind of incline is 0 degrees? Yeah, level surface. So what is this equation? I'll rewrite it. What does it reduce to? Yeah, for when it's a level surface, another way of saying that is the angle of the incline is 0. This formula reduces to just mu mg, because cos of 0 is 1. Okay? So this is just a level surface. As expected, right? This equation turns out to be what we expect for a level surface. What about when the angle is 90 degrees? Theta is 90. What is that when you're talking about a 90-degree angle? So you incline, keep increasing it until it's 90 degrees. What is that? What do we call that? Yeah, a cliff or a wall, right? Is it going to experience any friction when you're sliding down a cliff face? No, you just fall. There's no friction because you fall. So in that case, does that formula we wrote down, is it consistent with that? What's the cos of 90? We just said it earlier. What is it? You should know it, right? Cos of 0 is 1. Cos of 90 is 0. 0 times anything is just no friction when you're falling down from the top of a cliff. Fall straight down. So the point is the formula is consistent at the extremes, when it's level and when it's a cliff. Okay? So that's your final formula. If you want to write it out this way, that's fine. Friction is mu mg with the correction factor, where this is the angle given. It will be given to angle of the incline. Gosh, I can't sit like this. Angle of incline. Okay? Time is it? 9:27. Take a little 2-minute break. Stiffen up again. So I'll give it that 2 more minutes of break. Huh?
What's
that? You guys playing anyone soon? Should be easy. Okay, so just to summarize, this is really all you need to know, but the derivation, what I just did is called a derivation. That helps you understand how we got this formula, and therefore you understand the context. You can only use this on an incline. I'm not going to ask you to derive it, but you do need to know it. I'm not going to give you that on a formula sheet. So knowing how to derive it will help. What is it? Again, it's essentially the same equation you've been using in grade 11 with the correction factor. So that helps. Remember, there's a correction factor. And we haven't had to deal with it yet, but FG parallel, this is going to come in handy. Basically, it's just the force of gravity with its own correction factor. We'll deal more with that later. But what is FG parallel? Let's go back to the incline. FG parallel is this purple component, what I labeled with a purple vector. What is that? Well, if you go back further and you look at the incline, it's parallel to the incline. Purple component, FG parallel, is what pulls the block down the incline. Okay, so FG parallel is what's doing the pulling. The perpendicular part has no contribution. Only the parallel part. It's a fact of nature that whenever you have a force acting at some angle, if it's not parallel to the surface, it's at an angle, only the parallel part pulls it or contributes to the acceleration of the block. Perpendicular component, that's why we use perpendicular parallel component. The perpendicular part has nothing to do with accelerating this block down the hill. That block's going to accelerate down the hill. Due to what? Due to the purple vector, not the green vector. Why? It's a fact of nature. Why we use perpendicular parallel. Does the green vector play a part? Yeah, we just mentioned earlier, it does play a part. It's what keeps the block stuck to the surface, prevents it from floating up or sideways. It pulls it to the surface. Okay? So in simple terms, this is what you need for today. That one there. Keep using purple, it's hard to see. That one there. We'll come back to the second one. Just be aware of it. Okay, so you can work on those questions in the same handout that we worked from before, page 103 and 108. 1 to 5 on each.
Whoa.